Yeah, thank you very much for that, Janine. So as Janine mentioned, today I'm going to be talking through some components of my PhD work. And that was supervised by Dr. Jenny Gilbert, Dr. Stephen Lane and Dr. Amber Leeson at Lancaster University. My PhD was, as Janine mentioned, broadly split into numerous themes, all looking at particle-ice interaction. And today we're going to be focusing on the volcanic side of things, so how volcanic material interacts with ice systems. So this is just a brief outline of the talk this afternoon, pretty standard. I'll start off by discussing some of the introductory concepts, defining some of the key terms before moving on to a description of the methods. So this work was entirely lab-based, so using lab experiments in a controlled environment. So the method development was quite a critical component of this research. So I'll spend a little bit of time discussing that in detail as well. Then I'll move on to some of the key results, so some of the key findings from the study and the experimental work before rounding it off with some of the key take-home messages. So firstly, why are we interested in this? Why do we really care what ice is doing? Generally, in our current Earth system, many ice bodies are in a state of negative mass balance, which means that they're retreating. So we're losing ice mass. So it's converting from that solid ice phase to a liquid water phase. The state of ice is really important for our society generally, in terms of modelling how our Earth system will change. So here are a few examples as to why it's important to understand ice change in the current climate changes. These generally have an Earth science focus, but there are many more that are outside of the scope of this talk. So firstly, we've got increased hazards that can be expected with retreat of glaciers. So with warming temperatures, we see an increase in avalanche events, ice falls and so on. We also have rock falls. So as a glacier retreats down a valley, for example, it will expose those deglaciated valley sides, which can contribute to landslides and rock falls and slope instability. There's also a possible link with deglaciation and increased volcanic activity due to that ice unloading. We also have sea level rise, so it's important for us to understand how these ice systems are going to behave in the future in order to predict how our sea level is going to change, so we can mitigate against low-lying coastal regions and so on. And that's kind of similar as well to freshwater availability. So much of our freshwater is actually locked up in ice systems. So it's important to know how these ice systems are going to be behaving so we can predict this availability and possible trends with freshwater access. It's also ecosystem change, so forced migration of species, habitat loss, modifications to lake chemistry through freshwater input, for example, and finally ocean circulation. So this one is a broader scale potential issue here, where if you have input of fresh water into our oceans, it can disrupt these circulation patterns like thermohaline circulation, which can then subsequently impact the heat transfer over the planet. So we generally view ice systems as pristine environments. We all envision this kind of sparkly, remote area with, it's a very clean environment. But this isn't actually the case. Most ice systems will have surface particles that have been deposited on that surface. So it may be really kind of dispersed layers of particles or really thick layers of debris. And we'll discuss the different terms associated with them shortly. The importance of this is when we're trying to model and think about how ice is changing, we need to consider the presence of these particles, because ice with surface particles responds very differently to solar radiation and warming temperatures than if it was entirely clean. So these particles modify those thermal and optical properties of the ice. So we really need to understand ice behavior in this state so we can accurately predict some of the changes to these ice systems. The Properties and response of the ice is largely dependent on the thicknesses of the debris and also the particle properties. And we do also have a large range of particles that can be deposited on ice surfaces. So again, I've got a few examples here. This list isn't exhaustive. There's many other examples, but microplastics are an emerging area of concern. So these have recently been found in remote regions. Due to predominantly atmospheric transport and deposition onto the ice surfaces. We also have rock debris, which can be incorporated onto an ice surface through the scree slopes, valley sides, for example. Black carbon, brown carbon, either through anthropogenic inputs, so pollutions, or wildfires, for example. So a lot of the recent news of the wildfires is really important when we're thinking about cryosphere change, because they can travel extensive distances and then be deposited on these ice surfaces. So Greenland in particular has an associated darkening due to this black carbon input. I've also included meteorites here. So this isn't a particular particle that we have control over. They can be deposited all over the world, but if they are deposited on ice surfaces, they can interact with that ice, which I'll talk about in a little bit more detail soon. We also have dust, so soil-derived micrometer scale particles that again travel through the atmosphere that can be deposited on these ice surfaces and interact with the ice. And finally, volcanic material, which will be the focus of today's talk. So volcanic material can be deposited in a range of layer thicknesses, and there can be a range of particle properties associated with this material as well, which is why I've focused a theme in my PhD to understanding this in a little bit more detail. So before we move on to the volcanic side of things, I'm just going to provide a kind of summary as to how these particles actually interact with the ice and some of the fundamental processes at play. So I've started off with this very simplistic environment. This solid line here is just representing an ice surface. This is representing a clean environment, so we don't have any particles. For the ease of kind of explanation, this ice won't have any bubbles in either. This is a very clean ice system. We have solar input. So when we talk about ice melt in this research, we're thinking about how it's responding to that solar energy. And this energy at the surface is predominantly in the wavelengths 0.2 to 4 micrometers. So it's spanning across from the ultraviolet to the infrared region. Half of this, so the peak of this solar energy, is actually in the visible light region, so 0.4 to 0.7 micrometers. There's been a lot of work that has focused on assessing the absorption spectrum of water in all states, so solid, liquid and gas. And this has concluded that ice strongly absorbs those infrared wavelengths, but is generally quite transparent to the visible wavelengths. So the peak of solar radiation tends to travel through ice, and it doesn't really interact with an ice system. This changes when we add a particle onto the surface. So unlike ice, a particle can absorb in this visible wavelength quite strongly. This absorbs this peak of the solar spectrum, transfers that heat, that energy into long wave radiation, which can then be re-emitted by that particle and then transfer into the ice. So ice can now absorb that long wave radiation. So it essentially acts as a bridge between this visible interaction and infrared interaction, and it introduces energy into this ice system that would have previously been unavailable for ice melt. So without that particle, that visible region of the spectrum would not have interacted with the ice, but adding that particle creates this interaction. So I'm going to talk through a range of scenarios here, thinking about different configurations of particles. Just to note, these are very simplistic. Particles usually won't be arranged in such a neat way. They won't be spherical. This is just to help explain the general relationship here. But this is in a dispersed environment. So we have multiple particles that are transferring heat into the ice to initiate ice melt, as we can see by the kind of blue areas here are just denoting meltwater beneath that particle. If we add more particles to that system, they may start to interact, and the melt ponds may combine to create a larger area of melt. But if we continue to add layers to the system, we actually find that this balance between conducting heat to that underlying ice versus that increased absorption, it changes slightly because we've got a longer thermal pathway. So these particles at the top will be absorbing this visible light and conducting that heat through this layer. But this layer will be too thick to allow conduction of heat. So we find there's a point at which a thicker layer of particles actually insulate that underlying ice. So it's the opposite effect of adding a single particle or a thin layer of particles. And what we tend to see is, this is the original ice surface here. The surrounding areas will still continue to melt. They will be responding to atmospheric temperatures, solar radiation, but the ice underlying these thick layers of debris will be insulated and protected from solar radiation and the atmospheric temperatures. So on a smaller scale, we can create these like ice pedestals where we can see a smaller scale area has been protected. But on a broader scale, we can see some glaciers are actually being preserved. So our models may be predicting that this glacier would be retreating and melting due to increased temperatures. But if it's layered by these thick deposits of debris, that can actually insulate the ice in some cases. And this is a really lovely figure. Is to demonstrate this relationship. This is a glaciated volcano in Mexico. And this is essentially those ice pedestals that I was referring to. So we have this layering of volcanic material on the surface, which has essentially protected that underlying ice from the incoming solar radiation and warmer temperatures, whereas the surrounding ice system hasn't had that protection, has collapsed and continued to melt, which is why we see this outcrop of ice. This general relationship can be described by the Ostrum Curve, which is named after the first scientist who went in the field and identified this evolution between layer thicknesses. And it's essentially, on both graphs are showing the same thing, just in different regions. But on the horizontal axis, this is essentially the thickness of a debris layer. On the vertical axis is the ablation rate, so the melting rate. And you can see the maximum ablation is associated with these really thin layers here. And then with increasing debris thicknesses, we usually see a decrease in ablation as those layers are essentially insulating that ice. Some key terms as well. We've got this spectrum of this ice conditions where we have dispersed particles all the way to thick layer of particles. If we're considering an environment with layers, we usually refer to that as debris-covered ice, debris-covered glaciers. Whereas when we're referring to dispersed particles or a scattering of a very fine layer, we usually refer to that as dirty ice conditions. And it's the dirty ice conditions which generate the most uncertainty. So this enhanced ice melting regime is the least understood. When generating these curves, either in the field or through modeling techniques, it's usually the area with the highest uncertainty, or it's the area where the values have been estimated as the data can't actually be collected in the field. So I'm just going to describe some of the features that we can see on these ice systems as a result of these different ways of particle ice interaction and this different rate of ablation. It's going to be quite brief because this isn't the focus of today's talk, but it does provide some useful context for the results, which is why I've mentioned it here. So firstly, we have cryokonite holes, which are referring to these figures here. And it's essentially where you can you see this like hole that forms on an ice surface as these sediments on the surface have essentially aggregated together absorbed solar radiation, melted that underlying ice, moved downwards to create that hole, which has the sediment at the bottom. It's filled with water and it can actually host life. So we see algae growing on these glaciated regions in these cryokonite holes. On a broader scale, we have weathering crusts, which is referring to like a large scale region of rotting ice. So ice that is in the stage of melting. So we can see up here, we've got these like hollows, topographic hollows, and this is a schematic here from Cooper et al, where we can see these cryokonite holes have become embedded in this overall weathering crust surface due to this ice ablation in these dispersed particle environments. This ablation can also create ice cliffs, which is useful when thinking about runoff on these glaciers. And finally, there's this concept called lost meteorites, which I personally find really interesting. And it's basically Antarctica is a really useful region to collect samples of meteorites because it's a desert, it has very low weathering rates. So when you collect those samples, you get a pretty good analysis without having to include alteration processes that are occurring on Earth as well. However, the amount of iron-based meteorites, so meteorites with a high thermal conductivity that have been found in Antarctica, is much lower than that would be expected based on a global inventory of where these meteorites are falling. It's very rare to find iron-based meteorites in these regions. And this is essentially hypothesized to be due to that high thermal conductivity, allowing for a very efficient heat transfer between these meteorites into the ice. And because they're dense, they melt downwards and they're essentially lost from the surface. So there's been quite a few studies that have been thinking about this process and how we can model and work out where these iron-based meteorites end up. And some of my PhD work has looked into this as well and modeled and used experiments to see how these high thermal conductivity particles are moving through ice systems. Okay, so now moving on to a more volcanic focus. Why are we interested in volcanic particle ice interaction? Well, out of all of the examples of particles that I mentioned previously, volcanic material is the most diverse. So the behaviors that have been observed in the field are highly complex, highly varied. There's little consistency between each finding, and it's generally associated with the fact that the deposition of volcanic material is complicated, and we have spatial variability in thicknesses. We have a high variability in particle properties as well. But we need to know how these this material will interact with ice, because 20.4% of our current volcanic regions are topped with permanent snow or ice cover. So it is a common environment that we really need to understand better. So because of this kind of uncertainty with some of the results and variability that are found in the field, my research looked at trying to understand this variability in a little bit more detail. So looking at the dispersed setting, as that seems to be under-researched relative to debris-covered glaciers, and also looking at this volcanic particle ice interaction in a controlled setting. So trying to remove any of those extra complexities that kind of mask some of the processes involved, so we can fully understand what is exactly happening here. So I'm going to talk through the methods now for the research that I've completed. This is all entirely experimental based. We adopted a systematic approach and to kind of build up an inventory of processes that are occurring at this very micro level scale. So we're looking at the individual particle rather than the broader layer thicknesses as I previously described. So we used an 80-watt white LED bulb to act as our heat source. So we deliberately chose not to try to mimic solar radiation. So we used a source of illumination that was in the peak of our solar spectrum. So it's in those visible regions. We used optically transparent ice to act as our ice body. and then use time-lapse imagery to record the response of ice after placing a particle on that surface. So we imaged the ice every 5 minutes, which allowed us to create movies and analyze some of the micro scale processes that were occurring. So why did we choose optically transparent ice? This clearly isn't the reality. Most ice in nature is bubbly, but we decided to create this optically transparent ice to try and reduce the complexities associated with the system. So it would reduce ice radiation interaction, as the ice wouldn't have any bubbles or interfaces that might reflect or scatter the light. And it would also allow us to use that technique of time-lapse imagery. So we could image the cross-section of these ice blocks. And if they were bubbly ice blocks, we wouldn't have been able to get a good picture. We wouldn't have been able to see the level of detail that we did end up looking at. This was a very time-consuming process to create. Each ice block took around 1 to 2 weeks to form. And we essentially encouraged a very slow growing ice system that preferentially grew in one direction. So water is a very unique substance in that below 4 degrees, the relationship with density and temperature inverts. So colder material rises and warmer material sinks below this 4-degree threshold. And this is why in nature we see lakes have that frozen surface, because the cold water has risen, which is why it freezes at the top. The problem with that is if you've got this frozen surface, any air bubbles, any impurities that are within that water become trapped. So when that's freezing, the ice becomes very bubbly. So we froze the ice with side insulation. So it froze along this gradient here. So that would concentrate any trapped bubbles in one region. We had roof insulation to try and discourage this top frozen layer forming. And we also had a magnetic stirrer that disrupted that thermal stratification as well to try and disrupt that cold water rising. So the ice formed more uniformly rather than trapping the bubbles within. So we also chose visible illumination rather than an illumination source that mimicked the entire solar spectrum, because this would essentially isolate the effect of particle heating. So as I mentioned, ice is transparent to visible radiation. So if we illuminated an ice block to this LED source, it shouldn't be interacting with it at all. Whereas if we then add a particle onto that surface, it would be absorbing that visible radiation, and any heat transferred into the system would be entirely due to that particle ice interaction rather than the ice melting independently or interacting with that radiation. So this is the spectrum of the light that we ended up using, which is, as I mentioned before, in the peak of solar radiation as well. So it's a very important component at the Earth's surface. So this is just a schematic of the experimental setup. It took months and months to perfect. We essentially have A here, which is showing the LED illumination source. So this was overhead to try and mimic these natural conditions where a particle is illuminated from above. We have panel E here, this blue region. This is where we placed our optically transparent ice, and we then would place the particle on the surface here. We then captured the response of this particle and ice interaction using this time-lapse imagery camera here, using this very sophisticated periscope system that was attached to the freezer surface using tape, but it allowed this region here to be viewed through cross-section. There's quite a few other complexities with the setup that did take a while to fine tune. For example, we've got this fan at the bottom to circulate air within the freezer to try and disrupt any thermal stratification. We have this mirror to try and reflect away any incoming radiation. So that particle was only heated from above. It didn't then interact with illumination reflecting back upwards. And this was conducted, so I should have mentioned, this is conducted generally in a freezer here. And this was operating as close to 0 degrees as possible. There were some fluctuations, but generally it was just below 0 degrees. This is just a photograph to put this into context. I think sometimes it's easier to actually see photos. As you can see, this is the mirror system, which acts as the periscope. The camera viewed into this mirror, which then viewed into this cross section here. This is an optically transparent ice block, and then this is the LED radiation source. So once the method development had been perfected and we were happy with how things were going, as I say, it took months and months of testing. I conducted a series of control experiments, and this was the first theme of my PhD, where I essentially created an inventory of behaviours related to different particle properties that I deemed most crucial in particle-ice interaction. So these were the properties that have been described in the literature as having importance, or the particles that the properties that have been disregarded. So I first looked at thermal conductivity of the particles, so how efficiently it can conduct heat through that particle to the ice. Looked at the density, as that had previously been disregarded in the literature. Looked at the particle albedo, so how reflective the surface is, so how much energy it could absorb. And then I looked at the particle diameter. Again, this was disregarded in the literature. So these are just some of the images that came out of this series of control experiments. This is probably one of my favorite images that I've generated during my PhD. And this is just a Delrin particle that moved downwards into the ice. So it's kind of contained within this region of meltwater here. So it's melted the ice, moved downwards, and it's continued to melt the ice. This is looking at the thermal conductivity properties. So these are both brass particles. And as I mentioned before, with the lost meteorites, these were used to produce some kind of data on how these thermally conductive particles actually move around in ice systems. So you can see they started on the surface, they're denser than meltwater, they've transferred heat into the ice and then moved downwards. This is an experiment that looked at the albedo of particles. So you can see this is the white one, so a high albedo. This is an unpainted brass particle, so I refer to that as an intermediate albedo, and then the low albedo particle here. And I essentially set these ones off like a little race and seeing how they could move downwards through the ice, which was pretty interesting, but the results were pretty logical. We have the high albedo particles remained closer to the surface, whereas the low albedo particles melted the ice at a faster rate than the other two. Then finally, this is just a graph showing some of the data from the experiments looking at different diameters. And we did see some diameter dependency to the particle-ice interaction. So as part of the interpretation of results, so obviously I generated a lot of images with each experiment, and they lasted around 24 hours to a month, depending on the property I was investigating. In combination with that, I looked at the particle velocity. So when these particles were moving downwards through the ice, I could calculate the speed at which they were doing so, which I then used as a proxy for ice melt. So this allowed comparisons between different experiments and also within the literature as well, where they've used a similar approach. So I used 4 different techniques to look at the velocity. So I calculated an overall velocity, which was very simple. It assumed a linear behavior, which was not the case. So this is why we didn't just use the overall velocity. I also used the incremental velocity. So this was a point-by-point basis. So every 5 minutes, I worked out the velocity change. And this is shown on the graph here by these spikes. Number 3, looking at the smooth velocity. So I created a moving average to kind of show the general trends. I didn't want to remove all the fluctuations, as that was an important tool, but it was useful to see if there were any general trends throughout the experiment progression. And then number 4 was creating a simple melt model to model the particle velocities. And this was used mainly as a tool to help with my hypotheses when I started my experiments. And it essentially relates the lamp power density, which is equivalent to the solar input, for example, the albedo of the particle, so how much energy can that particle actually absorb, and then the latent heat of fusion, so ice melting. And that produced some modelled particle velocities as well. So for my volcanic series of experiments, I completed 34 experiments. I looked at single particles and a scattering of particles. The properties were varied systematically. They were all less than 12 millimeters in diameter. They all had a low thermal conductivity relative to ice. And then I differed the density, the porosity, and the albedos. So the compositions were the trachyandesitic cemented ash clusters. So these are from Iceland and are shown in this figure here. These were the first, this was the first material that I used in these experiments, and they're referred to as cemented ash clusters because they essentially, it was actually fine-grained material that combined to form a single particle, but it combined in the storage container. So it wasn't aggregation within plumes, it was just in the storage container, and these particles had essentially cemented together. And whilst they were interesting, they actually broke up when they became saturated. So they didn't really give much insights to the behavior of single particles. So much of the work was focused on the scoria and the pumice from Chile and Mount St. Helens, respectively. This is the scoria particles. You can see it's very dark in colour. So this was representing a low albedo particle. It was also denser than meltwater as well. So we knew it would probably sink. C is the rhyolitic pumice. So this is light in colour. It has a high porosity, so a lower density as well. So I'm now going to talk through some of the results. Generally, the main kind of overarching finding would be that all volcanic material that we used did induce some ice melt when subjected to this visible illumination. So remember, this system is in conditions that mean that the ice is stable in its solid form. So any ice melt that we saw, we knew was associated with that particle heating effect. And all of the volcanic material that we looked at did induce that ice melt. The results generally supported the existing literature as a range of behaviours were observed, and this reflected the complexity of particle-ice interaction. And there was also strong agreement with some of the control experiments. So we found that there was this kind of sorting mechanism and movement of particles within ice that was highly dependent on the particle properties. So that was also seen when we looked at the volcanic material. So we saw that the denser particles were able to move into the ice, and the lower albedo particles were usually associated with that higher rate of particle movement. So I'm now going to talk through some of the results in detail, first looking at those from the individual particle scale, and then moving on to a scattering of particles. So firstly, the fundamental particle behaviours. So as I've mentioned, we have this change in behaviour depending on the particle density. So our scoria particles were much denser than the meltwater. They transferred heat into the ice, produced meltwater, and then sunk in that meltwater, and then continue to sink downwards in this melt pathway. So you can just see the kind of outlines of this here with the laser pointer. We also had, as predicted, the case of the pumice particles, where they remained floating in surface meltwater. So even though these had a high albedo, these were still associated with quite large volumes of ice melt. So they were capable of melting the ice. There were further complexities to these two fundamental modes. So this figure here is actually a scoria particle. And prior to the experiments, I did a test experiment to test out those densities. So I put the particles in a beaker of cold water and just saw what happened. And they all sunk regardless of particle size. So this one is a 1.5 millimeter particle. And I knew in test experiments, this should be sinking. So with a lot of research and many experiments showing the same results, we deduced that this was likely held at the surface due to surface tension effects. So this particle was being held up due to the smaller sizes and a lower density contrast with the meltwater. This is an even more complex version. So again, this is a 1.5 millimeter scoria particle. So theoretically, it should be sinking, but it was held up at the surface through surface tension. But what we see in this particular photo is multiple drainage events, basically. So the drainage of the meltwater has pulled down these particles into the ice system, even though it's floating. And this is basically the active heating area that particle is continuing to melt the ice, even though it's being pulled downwards. These results also showed that the behaviours that we observed was highly sensitive to external conditions. So surface tension, as I've mentioned, but also temperatures. So we were constantly monitoring the temperature of the system, and even a 0.1 change in temperature was associated with quite a dramatic shift in behaviours. So another key finding was looking at how volcanic particles actually transfer heat into the ice system. And this is why the control series of experiments was really useful, because this helped with the interpretation of this. And it's essentially shown that these volcanic particles transferred heat into ice and drove ice melt mainly through convection processes. And we could identify that because this is the volcanic example here, and this is a brass particle. You can see in the case of a particle with a high thermal conductivity, it generates this melt pathway that's relatively narrow and mimics that particle diameter. And that's because it's got a high thermal conductivity. It's very efficient at transferring heat into the ice below through that conduction pathway here. So melting is mostly at the bottom of the particle, and it's driving that particle downwards. In the case of the volcanic material, as I mentioned, these all had a lower thermal conductivity relative to ice, so we're considered as low thermal conductivity particles. That means they're less efficient at transferring heat to the underlying ice. So it's likely that this top surface here was warming up with continued absorption and driving strong convection systems in the meltwater above it, which resulted in this kind of rounded base here and a wider melt pathway. And this was consistently observed with the lower thermal conductivity particles. So with the microplastics as well, showed the same kind of wide melt pathway feature. So this suggested that in terms of the volcanic material, it was a convection-driven ice melting process, whereas the higher thermal conductivity particles, like the iron-based meteorites, for example, was driven predominantly by conduction processes. So another key observation was the loss of fine-grained material into the ice system. This is quite logical, I guess, when you think about it, but it produced really interesting results. And we saw that in this example, we would have added this one particle onto the ice surface. So remember, this is an assessment of individual particles. As I added that on, there was a dusting of particles. So we either lost mechanically from the particle surface when it was introduced or during that active ice melt process. So that essentially introduced multiple absorbing surfaces into the system. So we saw this particle, as it was denser than the meltwater, that started at the surface here, moved downwards through the ice through active ice melt, and then was melting the ice internally. But the fine-grained material, which you can kind of see here in these regions, they stayed floating at the surface and created a large surface meltwater pond. So even though the target particle had moved away from this surface location, you can see here, we've got refreezing processes in between. We had these two areas of melt that were active and stayed active for many days until we eventually turned the illumination off and ended the experiment. So we can see that here we've got these two kind of focus points of melting. From this is a result of the active heat transfer from this particle, and then this surface meltwater here is associated with the fine-grained floating material. This basically showed that volcanic material can very effectively melt ice in these dirty ice conditions where there's dispersed or a scattering of particles. So one of the most interesting observations that we saw, which wasn't actually a focal point of our experiments, it was more a secondary result, was this particle fragmentation process at the base of these particles. And this was seen in every single composition, at least once, except for the pumices. It was observed in every single experiment as well. So it's clearly a common process that I hadn't previously thought about prior to the experiments that we observed consistently. So you can see here, this is the fragment that has broken off from this main pumice here. And then this is a scoria particle as well. We've got the fragment that's broken off here. And this was observed in all cases of the pumices. So the working hypothesis for this is based on freeze-thaw action. If anyone has any thoughts, I would be more than happy to hear them as well, as it's still a kind of work in progress here. So this is just a schematic that describes the process that results in this particle fragmentation. So I'm going to be referring to the pumices here, as this was most common with them. And we think that was likely due to the porous nature of the particles. So we hypothesized that the pumice was placed on the ice surface, the illumination was turned on, that pumice transferred heat into the ice system to generate meltwater. However, that meltwater likely immediately percolated through the pore spaces at the base of that pumice and saturated that kind of basal region of that pumice. We've talked a lot about heat convection from the particle, conduction through the particle, but we've not yet mentioned heat transfer that's also happening in the ice itself. So we have these thermal gradients. If a particle is transferring heat into the ice, that heat will still be moving along that gradient. It will cause ice melt if it raises that ice temperature above its pressure melting point before the heat is conducted away. But there are some instances where the heat can be conducted away prior to it raising above that melting point, or it can cause refreezing. So this is what we think happens here. So that pumice is in direct contact with the ice, and we have a thermal gradient within the ice that is taking heat away. So the heat that is being transferred into the ice is then being removed by the ice. And we suggest that that causes this basal region, the meltwater, to refreeze. So we're removing heat from that system. They're also very thermally insulating particles. So the base of the particle will also likely be the coldest region. So that freezing of meltwater will result in an expansion of the meltwater in those pore spaces, which we suggest leads to fracturing and then subsequent fragmentation at that base. So when that particle continues to transfer heat, it is always a balance between heat in versus heat out from the system. But in this condition, in some of the conditions, the pumices were able to generate more meltwater, create this meltwater pond, and that's when we first observed these fragments being introduced into the system. So when that pumice started to float, this smaller fragment essentially broke off and started to move downwards into the ice, which was suggesting active heat transfer as well from this pumice fragment. So one question that we do have, though, is these larger particles, the kind of main particle that we put as the kind of focal point of the experiment, they remained floating in the meltwater, whereas these smaller particles, they were usually less than 3 millimeters in size, they moved downwards. And this raised a question about the density evolution of these pumices in this meltwater system. And this has been a focal point in the literature for many years, so how pumices absorb water. So much of the research has been on sedimentary environments, in ocean environments. How long can these pumices essentially stay floating before they absorb that water and then sink? And some work has demonstrated that actually they can remain floating for months to years. And the length of time that they remain floating is usually dependent on the size of the pumice and how connected the pore spaces are. Generally, we see that the smaller pumices absorb the water faster and can actually, in some cases, reach full saturation immediately. So that's what we suggest happened here. We know that, or based on our kind of suggested hypothesis, we know that this basal area has had some interaction with meltwater anyway. It's been absorbing that meltwater, which has resulted in that freeze-thaw action. So we suggest that this small kind of fragment is already fully saturated, which is why it can move downwards into the ice, whereas this larger particle is not experiencing full saturation at this point. So the density is not sufficient enough for it to sink. So this kind of raises questions as to how the particle properties can actually evolve with ice interaction as well, which I'll talk about more in a minute when we think about modeling these systems. So I'm now just going to quickly show the combination of behaviors. So this will be a time-lapse image, time-lapse video, sorry. This is the cross-sectional view that I mentioned that we looked at. This is the original ice surface here, so we can see it is slightly undulating. The ice is much of this frame here. And then these like darker regions are the scattering of scoria particles that were added onto the ice surface. So in this experiment, most of them were fine-grained. We did add randomly some larger particles, so up to 3 millimeters, but they were still relatively small in size. And each frame is representing 5 minutes. So we can see immediately we have quite a lot of change to the ice system. We have many particles moving downwards into the ice. As they're denser, they've created that meltwater and sunk in that meltwater. We also have some particles that are floating at the ice surface. We can see some here. And then this growing surface meltwater pond that continues to grow in size throughout the experiment. We can see some individual melt pathways here. You can start to see some differences in the kind of reflection of light here. So many different things going on at once, which combine some of those results from the individual particle experiments. So this is just a photograph, a static frame of the same experiment. This was taken with my phone rather than the time-lapse imagery, which is why it's a little bit clearer. But we can see many processes going on here. Generally, it's very active. We are seeing a lot of ice melt induced by this dispersal of volcanic material. You can see this kind of clumping, this clustering of the finer grain material here to create this larger region of melt. And then there's many individual melt pathways. So I don't even think this picture picks up how many individual melt pathways were created through these individual particles sinking into that ice system and melting the ice internally. We can also see lots of particles that remain at the ice surface to create this surface region of melt. So this is a plan view of the same style of experiment, so scattering of particles. On the left is looking at these optically transparent ice systems. We also compared them to opaque ice just to think about the information our experiments were giving us, was that relevant to the natural system? Generally, there were a lot of similarities between the two. The same fundamental behaviors were observed. So we saw sinking motion and floating behaviors. We saw the same kind of convection-driven ice melt, loss of fine grain material. So many of the key results were applicable when looking at these opaque ice systems. You can see as well, some of the features are also relatively comparable. So at the beginning, we've got these more isolated areas of melt. So these are very similar to the Cryokonite holes that I mentioned at the beginning, where you have And these sediments, in this case, volcanic particles that melt downwards to create these holes that can be responsible for algae blooms and algae growth. The surface continues to become scarred as it continues to melt. And this is kind of comparable to that weathering crust environment where you have this rotting ice surface that's melting in many different places. The same features were also observed looking at the opaque ice block. We can see this kind of central region of ice melt in both views here. And that's where a lot of the finer grain floating material actually accumulated together to form a more concentrated region of ice melt. So there are redistribution processes at play as well. So I've brought this back to that simple melt model that I mentioned at the beginning, thinking about the particle velocities, mainly to use as a tool to provide discussion on the issues with modeling these environments. So as I said at the beginning, modeling ice change in response to climate change usually doesn't really include these ice states, whether that's debris covered or dirty ice environments. However, more work has focused on incorporating thick layers, so that insulating regime, into the models. These dirty ice models, so the regimes I've just discussed with the dispersal of particles, are really not very well developed, and they've not been included in these models much at all. I am not a modeler, so this PhD, this work didn't, necessarily provide solutions to some of the problems with dirty ice modeling. But what I hope it has done is provided some information as to what uncertainties we need to tackle, what assumptions may not be applicable when modeling these systems. So just for example, with this very simple melt model that looked at the particle velocity, we can see some general agreement here. So this is the 12mm cemented ash cluster. But generally, we're seeing that the modeled trends are underestimating the amount of melt. So in reality, we're seeing more melt than that being modeled in these conditions. There's also seems to be a size discrepancy between the particle sizes as well, which is something that we observed. The smaller particles, the 3mm particles, seem to be the most optimum when looking at the single particles, and then the finer grained material was the most effective at melting the ice and moving through the ice system. This doesn't take into consideration the evolution of particle properties. So as I mentioned, with the pumices, for example, we have that increase in density as the particle becomes saturated and absorbs some of that meltwater. And this is lightly reflected by the simplicity of assumptions. And these assumptions that were used in this simple melt model are also very common in other types of models in the literature review. So they're based on these energy balance equations that assume that the ice is at 0 degrees, so it's at its melting point. Now, if you remember, one of my key findings when we looked at the particle behavior was that these systems were very sensitive to temperature changes. So very subtle changes in temperature changed the way that this particle ice interaction was occurring. So this assumption that it's at pressure melting point is definitely one that may not necessarily be representative of the reality of this interaction. And I hope I've demonstrated that it's a very complex system as well. So I know this example is very simple, and the ones in the literature are much more developed and incorporate a few more parameters than just the albedo, for example. But still, the results are showing many different complex processes that are occurring. Another output of my work was it enabled me to develop this basically flow of processes. And some of the work I still want to do is develop these kind of processes that I've observed into conceptual models and thinking about how these systems behave. So this brings together all my PhD work. So it has components, so section 4 and 5, we've not really discussed in today's talk, but generally looking and analysing these results enabled me to make a kind of progression of a typical ice system and relate it to the particle properties. So this lamp on here is essentially representing the illumination becoming present. So the dawn is breaking in the natural system. We have these particles on the ice surface. So we need to think about this initialization of melt. And my experiments identified that the thermal conductivity was one of the key properties here in determining how this initialization of melt was occurring. So if you have this low thermal conductivity, it's warming that top surface, which is driving convection and driving convected heat losses to the atmosphere as well. Once the particle has initialized ice melt and produced meltwater, the next stage is, will that particle flow or will it sink? So quite logically, that's related to the density, which appears to be disregarded pretty much entirely in the literature as an important property of these particles. Obviously, high densities will usually be associated with sinking behavior. Low density will be associated with floating behavior. But we have this extra complexity here with the intermediate densities. So those regions where we can see surface tension effects, either holding a particle up at the surface. Then section 3 is just thinking about the evolution of properties. So in the case of pumices, are they absorbing more water into that pore space? Do we see that change in density? And then that changes the way it behaves in the system. So it may have that associated increase in density and then sink into the system and melt the ice internally. So this is just an example as to how some of these outputs are helping us map the movement of particles in the ice system as well. So just some of the conclusions. Hopefully I've convinced you all that in these dispersed, dirty ice conditions, volcanic particles can very effectively melt the ice. And this actually contrasts with how volcanic particles are viewed in the literature. So when we're thinking about layers, they're typically viewed as very insulating material due to that low thermal conductivity. But this series of experimental studies have shown that they are actually very effective at melting the ice. We've identified that ice melt is predominantly driven by convection-based processes, which is related to the thermal conductivity of the particle. We've observed that fragmentation of the particles is a common process, especially in the case of pumices. So that was observed with all experiments, and that introduced another absorbing surface into the ice, which further increased this ice melt, as did the mechanical loss of the fine-grained material from that particle surface. And that leads into this statement here that a single volcanic particle is rarely a single volcanic particle once it enters this ice, whether that's through particle fragmentation or mechanical loss of this fine-grained material. And finally, hopefully you can see that we can link some of these features, and this is some of the work that I'm trying to do now to develop this and linking it to features that we see in dirty ice conditions currently, so those cryokonite holes, weathering crusts and so on, and hopefully developing some conceptual models to understand thoroughly the processes involved in this particle ice interaction. Okay, that's everything. Thank you very much for your attention, and I welcome any questions.
Brilliant, thank you very much, Katie. So we have some time for questions.
You talk a lot of really nice and curious ideas. What is the role of the particle geometry? So the actual particles we're looking at that are quite irregular. How much of an influence do you think that has on melt rates?
Yeah, okay, so for the Zoom audience, the question was, what is the role of the particle geometry? And that's actually a really important component. So that wasn't necessarily identified as one of the particle properties that I originally looked at, but the results from my experiments showed, especially the microplastics, which is why I've not really included it today, that the thinner particles were much more efficient at melting the ice, basically, because that thermal pathway was much shorter relative to a kind of longer particle. So the geometries definitely have an influence. but I didn't do a systematic assessment in the same way as I did the other properties that I've mentioned.
Very interesting talk. I was wondering, your last one there, you were talking about comparing what you've done in your experiment with dirty ice conditions.
Yeah.
I guess it's a twofold question. One is this comparison done with natural systems and your experiments? And if it is done with natural systems, are you aware of any work that has looked through maybe sectioning ice samples to look through, particle locations, shape, size and type, and relation with potential melt pathways or melt shapes that could be compared to experiments?
Yeah, so for Zoom, the question was about the last point of the conclusion, so linking some of these experimental results with those observed in dirty ice conditions and whether that's linked to natural systems, and if I've looked at how, if there's been any work as to looking at a cross-section of ice and looking at if we can identify some of those features through that cross-section. So my answer to the first part is I'm trying to link it to natural systems, but obviously I'm mindful that this is in a laboratory environment. The ice is optically transparent, so I'm still in the process of wanting to bridge that gap a little bit. I've identified initial thoughts as to why as some features that look very comparable. So the weathering crust and cryokonite holes that we do see in nature were features very alike to what I observed in my experiments. In terms of looking at the cross sections, the inglacial regime, so in the ice, seems to be an area that's massively overlooked, especially when it's looking at ice ablation. So it's usually focused on surface particles or looking at layer thicknesses, for example. So the kind of work that may focus on these sorting mechanisms and looking at that cross section in the ice itself seems to be lacking, which is why I think my work, I was quite happy to spend a bit of time looking at that inglacial regime, especially because there's been work like the Evet et al. Study, which has been talking about lost meteorites into that inglacial regime. Clearly it's a system which is quite dynamic, but to my knowledge there hasn't been much focus on that particular area.
Yeah, I enjoyed it. It was awesome. Encouraged lots of thought. Just if I understood everything that you said that the main mechanism that you were considering was thermal conductivity of the particles for the melting of the ice too. So just, and I think you mentioned earlier on that you didn't think, or density of the particles are kind of largely being written off too. For water, in that you get pressure melting of ice. I just wonder, particularly for like an iron meteorite, for example, these lost meteorites, whether the weight of that could create pressure melting there. And I just wonder why density had kind of been written off, because I guess in experiments, comparing those two, the thermal conductivity and the density might actually be related too, so it's difficult to separate out. So yeah, is pressure melting just because of the weight of the particle, the density of the particle? Why is that written off as a mechanism?
Okay, so for the Zoom viewers, the question was about the balance between different properties and their importance, so thermal conductivity versus density, and why density is generally being written off. To answer your question, it's very confusing. There's a lot of different processes going on, and one of the benefits of the lab system was being able to isolate the different properties, but even so, I couldn't isolate them fully. So I wouldn't necessarily, I think the way of viewing it is like an evolution of properties and their relative importance. So I think to start off with, the thermal conductivity and albedo is definitely one of the most dominant properties, but I think that shifts to density once meltwater has been introduced into the system. But even so, it is hard to separate the two, because usually low dense particles are associated with a low thermal conductivity and vice versa. So it is hard to isolate them. I think generally it's being density is being disregarded, not because it's been an active disregardment, but more that the work hasn't really focused on environments where it would matter. So as I said, much of the work has been looking at the boundary between that peak ablation and then ablation where we're in that insulating regime. So we're thinking about layers there. And in that environment, the layers aren't necessarily, and the density isn't necessarily as important, because much of the work is considering that superglacial environment rather than movement of particles down into the system.
I could just quickly follow up on that. So, or has anybody else done any experiments where you just switch the light off, so you take away the heat source, so you remove that thermal conductivity part and just see whether the density, whether the particles continue to move?
Yeah, so for the Zoom viewers, the question was, has any experimental work looked at basically just turning the illumination off to see if density can be driving that pressure melting? I have done that quite a lot. It wasn't necessarily a focal point, so I didn't necessarily note the behavior. Most of the experiments, I would turn off the illumination at the end to see if the meltwater refroze or if it remained as meltwater, because it was a useful tool in acknowledging whether that system was stable or not. So if the meltwater remained in liquid form, that would probably tell me that the temperatures were too high, and that meltwater probably wasn't a result of that particle heating. And in those cases, all the time, the meltwater refroze. So I didn't see any kind of density driven processes, but equally, I wasn't looking for it necessarily. Yeah.
Okay, well, I've got questions, but I'm going to ask you about them.
Sounds good.
So thank you again to Kate.
Thank you very much. How are we doing? Fine.
Oh, we started late.